Never trust an atom, because they make up everything. No, really, they make everything up, including this tasty, tasty chocolate chip muffin. And they make you up, too. It makes up everything, all matter, all stuff, anything you can touch or see or feel. It's all made up of atoms. And just to get an idea of how small atoms are, the average human, like an adult human, carries, like a 70 kilogram human would have 7 octillion atoms making up their body. Octillion atoms. That is a 7 with 27 zeros behind it. That number is unfathomable. That's 7 billion atoms in a single adult. So these things are really, really tiny and delicious. But really, what is an atom? That's the question we're going to try and tackle today. No, trust me, scientists have been working on this for a long time. A long time. Hundreds of years, scientists have wondered what makes up stuff. They've been asking questions since early Greece, like it's just a fundamental question to nature. What is this stuff? Where does it come from? So, again, scientists, we've been working on it. We've been slowly coming up with all the different pieces of the puzzle, slowly putting together the atom, and it's what we call atomic theory, our understanding of what an atom is to date. So, what really is an atom? Let's have a peek. Let's have a look at my muffin droppings, if you will, to kind of come up with an idea of it. Now, there's some bigger pieces that, made of more atoms than the smaller pieces. But the idea that I want you to start thinking about, and this is what some of the early philosophers started thinking about, if I continued breaking apart this piece of muffin, it gets into smaller and smaller bits, and eventually, will there be a building block that makes this up? Is there an ultimate piece that it can no longer be broken down into? Several philosophers used to think so. They used to think that eventually, if you kept breaking things apart, they weren't really worried about muffins at the time, but the thought experiment that was proposed was if you had a rock, you can break that rock in half. You can break it into 2 different pieces. And then those further pieces, you can take them and you can break those pieces in half. And then further, again, those pieces that you have left, you can break them into half, and then into half, and then into half. And eventually, you end up with smaller and smaller pieces. They thought that perhaps, eventually, there would come a point where you could not break it in half anymore. That you would be down to the fundamental building block of all matter, of all stuff. And one Greek philosopher named Democritus called that fundamental building block atmos. Think about that. If you keep breaking something apart, there's only 2 possible outcomes. One, eventually you find that ultimate building block. Or 2, the other possible outcome is that they keep getting smaller and smaller and smaller and smaller indefinitely. And that one is more unlikely, because if these keep getting smaller and smaller and smaller, and they can become infinitesimally small, so they have no limit on their size, if the building blocks of the universe were made of things that were infinitesimally small, how could we possibly have something that's finite? How can we have something that actually has size if it's made of infinitesimally small pieces? So the only logical conclusion really was that there must be a building block, that it couldn't just keep getting smaller, or else you really wouldn't be able to build matter. Some of the first evidence that things were actually made of building blocks came from an experimenter named John Dalton. He was working with different metals and combining them with different things. And so, for example, he had some tin metal. And he was chemically reacting that with oxygen. he noticed something very interesting, that it always chemically reacted in specific proportions. So tin would always chemically react with oxygen in a 1:2 ratio. So if you had 13.5 grams of tin, it would always react with 27 grams of oxygen. And that kind of thinking led to the fact that, well, there must be building blocks. It must be one tin atom reacting with two tin oxygen atoms. So this was the first real evidence that, hey, matter was actually made of a unit of something. And again, that comes from the idea that there's a basic ratio that chemicals will react with each other, and that's what we find with like H2O, for example. In today's modern understanding of atoms, we have two hydrogen atoms reacting with one oxygen atom, always in that ratio when you're forming water. So again, he examined that and he noticed that there must be a building block that makes it up. That was our first piece of the atomic theory. So cool. John Dalton found out that there must be building blocks. The next thing we needed to find out was, cool, we know atoms are there. What are they? We still don't have an answer to that. So we started working a little bit more. And J.J. Thompson was the next person to come into play. He was working with cathode rays. What a cathode ray is if you create a vacuum inside of glass, in other words, you suck all of the air out and create a really, really low pressure system inside of a closed gas container, and then you run some electricity through there. Once you start running electricity through there, you create an electric field that can produce a stream of particles. So J.J. Thompson noticed that the glass on the other side of a cathode ray would light up. It would glow. So there must be particles coming from there that's providing some sort of energy. So he correctly surmised that it must be some sort of particle. And with further testing, he came up with a couple of key pieces of information about these particles. One being that if you put a negatively charged plate, negatively electrically charged plate near the cathode ray, he noticed that the glow would actually shift away from the electron plate. So, and the answer to that, the reason why, is because just like magnets, electrical charges can repel and attract each other. Negatively charged particles repel other negatively charged particles. Positively charged particles repel other positively charged particles. And then positive and negative attract each other in the exact same way that magnets do. Like north repels north, south repels south, but north and south attract each other. And we'll find out even later that magnetism and electricity are the same thing. We'll dive into that more in the electricity unit. But so back to the cathode ray, when there's a stream of particles moving across this space inside of this glass, if you put a negatively charged plate near there, that stream of particles will be deflected downwards and away. So J.J. Thompson correctly discovered that the stream of particles coming from the cathode ray must be negatively charged. And then he went about calculating how big these particles were. He found out, doing some science wizardry and some math work, that the particle size for each of those individual particles streaming through there were 1,800 times smaller than the lightest known atom. So we knew that hydrogen exists, and J.J. Thompson just found that there was a particle 1,800 times smaller than the lightest atom that we know. There's something going on there. So he came up with the assumption that those particles must be part of the atom. So J.J. Thompson came up with what he thought the atom looked like. He envisioned the model like plum pudding, which is basically raisins inside of bread. I've got something better, modern. Chocolate chip muffin. So basically what he imagined was that the electrons, the particles that were making up the atom, were like the chocolate chips on the muffin. There were these negatively charged things that were all throughout this sea of positivity, he said. It must the atom must be neutral, because there's no way that you can have just negative things making up the universe. That'd be impossible. Remember, negatives repel other negatives. Everything, all of matter, would repel itself if it was only made up of negative things. So to hold this together, there must be positive, some sort of positivity associated with it. So he thought this muffin, this plum pudding, the atom, was this positively charged region of space. And then all in through there is all of these negatively charged particles, which which are now called electrons. So even on the inside of the muffin, of the atom, he thought there was just this space, this sea of positivity with negatively charged particles all throughout there. At the turn of the century, in the year 1900, one of J.J. Thompson's own students proved him wrong, proved that the plum pudding model actually doesn't work for the atom. So Ernest Rutherford, again, one of J.J. Thompson's students, he created another type of particle. He created something he called an alpha particle. Alpha particles were positively charged. So when put near a positively charged electric field, they would repel away. So he had these positively charged particles, and he's like, perfect. I can take these particles and I can stream them towards some atom. He proposed an experiment. And the idea was, if this was truly the model of the atom, then if he were to set up a whole sheet of atoms, so he decided to use gold because gold was fairly heavy, and it was very easy to turn into a very, very thin sheet, possibly only a few atoms thick. He imagined that if he could stream positively charged particles towards a whole sheet of them, then again, there's two possible results. The massive amount of positivity will reflect away all of the positively charged particles coming in. Or if the positivity was too weak, then the positively charged particles will go straight on through the atom. So assuming that either this whole thing was consistent and it was a sea of positivity, this whole space was positive, it would reflect away every single particle. Or if this sea of positivity was too weak, then all of them, all of his alpha particles would be able to go through and land on the detector on the other side. So when he started streaming them towards the gold foil, that sheet of gold atoms that he set up, most of them went through, but not all of them. Not all of them. How could he possibly explain that they didn't either all get deflected, or that most of them went through, but occasionally a small number of them would reflect back? The only possible solution to that is that there must be a core to the atom. There's a nucleus to the atom, and it's positively charged. So he came up with a new model for the atom and threw away the plum pudding model. He suggested that perhaps there was a core, a nucleus in the center of the atom, and then around the atom was the negatively charged particles. It was more like a solar system. So that's the solar system model of the atom, where, and this is the one that's most commonly used, like even in the show The Big Bang Theory, they show the solar system model of the atom as one of their symbols. We know now that that's actually not true. It's not complete, but it's much better. It's the next step in discovering what the atom really is. There is a core to the atom, and it is positively charged. All of the protons are in the center. So you have a positively charged proton-filled nucleus, and around the nucleus are negatively charged electrons. Protons, positively charged, core. Electrons, negatively charged, orbiting the core. In 1913, the next piece of the puzzle was solved through a gentleman named Niels Bohr. Now, Niels' work is a little bit above our understanding level at this point. He started, the world started understanding what quantum theory was. And now I'm not going to go into quantum theory because it's, as Einstein very adeptly described, quantum theory is spooky. So, what Niels Bohr did eventually find out was, and it was because he was challenging the idea that there's no way that an electron could possibly actually orbit a proton. If it were orbiting the proton, it would run out of energy really quickly and spiral inwards and then make contact with the proton. So what he found out using quantum theory is that the electrons orbit in very specific places around the core of the atom. They can't move any more closer, and they can move further away, but only in specific places. So if the electron was orbiting around the core of the atom, it can move out, but it jumps out to a higher level. And again, that doesn't make much sense when you think about it, because how can a particle simply move from one orbit to the next one instantaneously? But they do, and it's again really spooky, but it's a fact of science. We've observed it countless times. And so you have a proton, you have a core of the atom that's made of protons, and then Niels Bohr described these areas in which electrons must orbit. He called them valence shells. So imagine them as a shell around the core of the atom. That is where you will find, so like a sphere, that is where you'll find the electrons. And then there are other shells. There's bigger shells around the same group of protons. You have different shells, bigger and bigger shells of electrons that are all around it. Again, those are called the valence shells, and electrons can't exist in between those shells, only exactly on them. And this proved to be much more accurate, but not quite all the way. So what's the modern atomic theory? And you'll never see a symbol like this anywhere, because nobody really gets it. They understand the orbiting model, whether it's Niels Bohr's model of the atom or it's the solar system model of the atom. Those are the ones you typically see, which I still find really funny, that the Big Bang Theory, some of the brightest minds in science are using the wrong symbol for the atom. But here's what the atom actually looks like. To our knowledge so far, we're still developing this theory. This is our modern theory of the atom. This is the quantum cloud model of the atom. The quantum cloud idea is very similar to the valence shells, but the valence shells are specific regions around the atom. So depending on the atom, there's different regions that are around it. There's different clouds in which certain electrons can exist. And when we look at atoms using a powerful enough microscope, when we start observing them, we notice these shadowy patterns. And so far, this is proved to be the most accurate model of the atom, the quantum cloud. And as the atom gets bigger and bigger and bigger, these clouds become more and more complex, and they become really interesting. Let's summarize. First of all, we figured out that atoms must be made of some sort of building block. They couldn't possibly just keep getting smaller and smaller and smaller, because if you had an infinitely small object making things up, how can you possibly have something finitely large? So you can't have something big from something that is infinitely small. So no matter how many of them you have, they would still add up to be infinitely small. So there must be a building block. Dalton proved that. Dalton proved it when he started looking at how atoms bond with each other. He found that, like, for example, with tin and oxygen, the tin bonded with exactly 2 oxygens. From there, we had J.J. Thompson. He discovered the electron. Using the electron, he decided that there must be negatively charged particles that make up part of the atom. They were very, very tiny. So he imagined the Plum Pudding model, where there was a sea of positivity with a smattering of negatively charged particles inside of that sea. Rutherford proved him wrong, his own student. He proved that there, in fact, must be a nucleus of the cell using his gold foil experiment. He shot positively charged particles at some gold foil and noticed that occasionally some of them would reflect back. The only way to explain that is that there's a very, very, very tiny nucleus of the atom. In the very, very core of the atom, there is a positively charged space, a very strongly positively charged space. So all of the protons, the positively charged particles, were gathered in the core, and he guessed that around that positivity must be the electrons. And he imagined it like the solar system, that the electrons were floating around there. That was further proved wrong by Niels Bohr. Niels discovered that mathematically it didn't make sense for them to actually just orbit around, because they would very quickly lose energy and spiral inwards, and the electrons would all just gather in the core of the atom, and that didn't make any sense. So he, using some calculations with quantum theory, he eventually came up with the valence shell explanation for the atom, where it still had a positively charged core, but there were shells of electrons around the atom. Those were the places where electrons could be. Now we've further refined that idea of quantum into the idea of quantum clouds, so that electrons are in these certain regions around the atom. If you have the core of the atom, there's certain spots where the electrons could gather, and those are the clouds, the quantum cloud model of the atom. That's all for today. Thanks for watching. Till next time.